Hello and welcome again to my physics online video supplement series. Today's video I'm going to be doing a brief introduction to statistics as we will maybe use them a bit in our class and especially in our lab activities. This is really in some sense part one of a two-part video. Today I'm just going to go through the how do you calculate the relevant terms that we need, and then in the next video I will talk a little bit about how you might use them to set up comparisons between data and theory or between two data sets. This is not meant to be an extensive or comprehensive lecture over the topic. It's just meant to be a simple introduction and practical here's how you can go about it type lecture. So let's get into it. The first thing to note is that we are making some assumptions here. The big assumption that we're going to be making is that when you are taking your measurements, that there's some error present in the measurements and the error is random. It's not systematic error, it's just random. And as such, it can be said to essentially fall along a Gaussian or normal, standard normal or Bill curve. So we would say that it basically falls along a Gaussian distribution. And so that's sort of the operating assumption that we have here. And you know, maybe you are maybe that is all the error that is present. Maybe there's not some systematic source of error that needs to be further analyzed, and maybe there is. Even if there is some systematic error, you're probably going to also have some randomness for your uncertainty. So your basic procedure, I'll draw out here and then I will go through each step. So obviously before you can do anything else, you have to collect your data or make your measurements. So collect data or make measurements is the first thing that you will be doing. And so we kind of are assuming you've already done that step with whatever experiment it is that you're trying to analyze. Okay, so the statistics proper begins step one, compute the mean. So calculate the mean or average of these measurements. Step two is then to calculate the standard deviation. And I might add here that for a small sample size, properly the step three would be to get into figuring out what the t-distribution, what the t-score is, all that. We're going to kind of skip that step. Even though our sample sizes are small and therefore that would be an important next step, it becomes impractical to do this as a lab thing for your data analysis. So, you know, t-distribution would be next, but we're just simply going to sort of paper over that one for now. It's a kind of minor in this case. Step number three is calculate the standard deviation of the mean. And so this is part of why I'm okay with ignoring t-distribution, because sample size is kind of baked into this particular computation. Okay, and then step 4 would be used to compare results to theory or to other results. And the focus of today's video is basically steps 1 through 3. So this is sort of, you do this before you can get started on this process. Step 0 is. Step 4 is really for another day, next time, next lecture, next video. And that itself will have a few sub-steps. So to motivate all of this, let's say that you are going to measure the length of an object. It's just a simple measurement of length. Maybe the object happens, though, to be something like this sponge here, where it's kind of bent and wiggly and everything like that. And if you attempt to push a measurement on it, it deforms the sponge a little bit, especially if the sponge is wet, but even if it's dry, it'll tend to deform a little bit. So you decide to measure along the outer edge, like from here to here, for example, of your sponge. You get out your ruler and you put it up next to the sponge. Maybe you're measuring from here to here, maybe it's from here to here. You put it up next to your ruler, and this is what you see. So your ruler has large tick marks denoted in centimeters. It has smaller tick marks denoted in millimeters, and there's usually a tick mark to represent the halfway between 1 centimeter mark and the next. So you go to make this measurement and you say, this measurement looks like I have a length of, let's say, 12.4. If we were to count here, this is 1, 2, 3. This is the 0.4 mark. This would be 0.5. This would be 0.6 for what it's worth. And I can kind of look on here and estimate where this edge is lining up between these. And so maybe I say that this is 12.45 centimeters. Now I notice that it's kind of wiggly, it's kind of easy to deform and all that. So maybe I get a friend to double check for that. So my friend comes along and measures it, and my friend says, well, I actually measured 12.44 centimeters. And then I ask my next friend to measure it, and she says, well, I got 12.46 centimeters. And then the next friend comes along and tries to measure, maybe again 12.44. And then the next one, 12.45. Next one, this was number 5. This is number 6. Maybe this one gets 12.46 again. Maybe there's someone who comes along and gets 12.43, and maybe somebody else comes along and gets 12.48, etc. All right, so this was sort of like step 0 in this entire procedure. And so now we say, all right, what is the measurement of this length of the sponge? Maybe another friend comes along and says, gosh, I measured 12.61 centimeters. So this is a very large outlier. Okay, so now we go back and we question. It turns out that 1 through 8 all measured this length, and number 9 actually measured a wiggle out here, which is, far enough out that maybe their measurement just is different than ours, or maybe they didn't line up the 0 mark very well on the other end, or they could be at a slight angle or something like that. All right. So maybe we say, all right, well, this one can be thrown out for the reason that they measured something different than everybody else. But these measurements all purport to be of the same thing. So our first step then, coming over to our little menu, our recipe, after collecting the data, is to get a mean or an average. So the way that you calculate a mean in general, so let x with a bar on it be mean value or average value of the x sub i's, or x, let's call them sub j's for the individual measurements, okay, or indexes. All right, well, the way that you would calculate x from x sub I, or from x sub j, excuse me, is you would take 1 divided by n, then you'd add up all of the individual measurements that you are certain are valid measurements, like so. Okay, so this is your basic formula for finding an average. So if x represents the length of this sponge, then in this example, my average would be 1/8 of, let's actually write this down here where I've got a little more space. So find the average for the length of the sponge. And the way we would do that is, again, 1 over n. Well, there are n valid measurements. There are 8 valid measurements. And then I have to add up, it says add up all the individual measurements. So 12.45, 12.44, 12.46. This is 1.44 is supposed to say, you're supposed to say 12.4. Not 1.44. So 12.44, 12.45, 12.46, 12.43, and 12.48. And what you're going to get when you average all those is 12.45, as it turns out, 125 centimeters. Okay, so we've calculated the average value, and we've retained quite a few digits. Probably we would maybe want to round this off somewhere in here, and so x might be like 12.45 centimeters. All right, so we can circle our answer. All right, so that's the example on how to calculate the mean. The next step is standard deviation. And if you look on your recipe where it says calculate standard deviation, what this is basically telling you is the uncertainty of that measurement. So it's a measure or a metric or a number that tells you the size of. So it's a measurement of the uncertainty of your measurements. And the way that we compute it is this. There's actually a few different versions of it. I usually compute a sample standard deviation, and what that looks like is, for all of them you basically are taking a square root. For all of them you're basically doing a sum, and what goes inside the sum is the difference between your individual measurements and your average measurement squared. Now, depending upon whether you are doing a sample, a full population, or what have you, determines what goes in the denominator of this fraction. It begins with n, and if what you're doing is the full population, it just is 1 over n. If you have just a sample within a population, it's 1 over n minus 1. Because you're doing about 5 trials typically in your labs for a given thing, this 1 over n minus 1 is probably the way to go. All right, so that is the formula to calculate the standard deviation for a sample. In terms of what we have over here, our measurements, this formula will look like this. And this is going to take more than one line to write. Sigma is, and I'm just going to use parenthesis to use my square root. So to make a square root, you raise stuff to the half power. We have 1 over n, which was 8, minus 1. So this is going to be 1/7 of, and then we have to do our individual numbers. So first one was 12.45. From that you would subtract your 12.45, and you can include the extra digits if you'd like here. Square it. And then you add the next number, which was 12.44, and again minus 12.45 squared. And then the next number was 12.46. And you just, keep doing each of these until you've got all 8 of these numbers here, each time subtracting this mean. So I'm just going to say dot, 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 put a little ellipsis here. And so, you would compute these and, square each one, then add them, divide by 7, then take a square root. As it turns out, if you do that, you get something approximately equal to 0.0155 centimeters. This is in centimeters. Now, why is it that we do it this way? Why not just straight average the differences? Well, because the way that this term right here, this mean term, is defined, if I were to take the difference of that mean from each number that I've measured and then sum all those differences together, I would have sort of like a total difference, and so then I could divide by 8 and have, let's say, an average difference or average deviation as opposed to a standard difference or standard deviation. But because of the way that this term, this average, is defined, once I sum all those differences, I'll have some positive numbers, some negative numbers. They add up to 0 every time. To the extent that they don't, it ends up being round off error. And so the standard deviation allows us to sort of ignore that part or get around that part by squaring the differences first. So we square all the differences, then we add them all together. That means we're going to have a positive number. Then we divide by 7. We still have a positive number. We take a square root. For what it's worth, if you want to find an average deviation, the way that you would do that, so and this is kind of an aside, average deviation, which we often could abbreviate as this. It's given by 1 over n times the sum from j equals 1 to n of my individual measurement minus my average measurement, and then take the absolute value. So that also guarantees that you end up with all positive numbers and therefore don't end up with a 0 here. All right, but for the standard deviation sample, this is what this ends up computing to. Now, last little step here for today is to get the standard deviation of the mean. And this is fairly straightforward. to do once you've got the standard deviation. So let's say that your standard deviation was sigma. Standard deviation of the mean we might represent as sigma bar. And the formula for that is just that sigma bar, the standard deviation of the mean, is the standard deviation divided by the square root of the number of measurements that you've taken. So in this thing's case, as our example again, we'd say that sigma bar is 0.0155 centimeters divided by the square root of 8. And when I put all that into my calculator, I get 0.005489. So this came out to 0.005489 centimeters. Okay, and so that kind of gets us to the end of this procedure. Now there is one last thing that I want to show you in today's video. I've pulled open here Excel, and you could do this in Excel, you could do this in LibreOffice, whichever you'd like. And what I've done is I have, these are my indices, so I have my 8 measurements. I've typed the 8 measurements here, and then I've used Excel to calculate the average, the standard deviation, and then the standard deviation of the mean. And I really should maybe also format the cells to give the number of digits that I want to be shown, like so. Okay, and so the way that you do it is this. To get the average, you type equals average. So you just type the word average, you take a parenthesis, you select your data, so I just kind of click and drag, close parenthesis, and when you hit the enter sign, you have the average value. For this one, it's equals STDEV, standard deviation, and the .s is because I wanted it to calculate this standard deviation, not the population one where it's 1 over n. Okay, so obviously if it's 1 over n, I should get a slightly smaller number. So here actually is what would happen if I treated this like an entire population, slightly smaller number. But stdev.s is for standard deviation, stdev.p is for population. And then to get the standard deviation of the mean, I simply took the standard deviation that I calculated here, and I divided by the square root of 8, since that was the largest index, or in other words, it's the number of measurements I've taken. And so I'm showing you all this because this will make it a little bit faster for you to do these calculations, because you can just type the numbers in here and have Excel do the calculation for you. It's kind of good to do it by hand on occasion, and some of your labs will call for you to do that on occasion. But if you're not specifically having to do it by hand, it is kind of nicer to do via the computer like this. So that's all in this video, and of course in the next one we will look at what happens if we want to compare data sets using basically these results. For what it's worth, at the end you might state that the result of your measurement, so we'll call that result of measurement, is, and then we usually just use our mean plus or minus our standard deviation of the mean. So this is what's usually meant in this context. Technically, our result is value plus or minus uncertainty in value, but we're using our standard deviation of the mean as a stand-in here for our uncertainty. All right, so this was kind of a longer video just because there was more computation involved than normal. But I hope that you found it to be helpful, or I hope that you will find it to be helpful as you go through your course and as you do labs and so on. So thanks for watching, and maybe see you in the next video. Goodbye.